Hi, let's talk about a special case of motion with constant acceleration in one direction, and that special case is what we call free fall. Free fall is an object falling subject only to Earth's gravity. That means in free fall there's no air resistance, there are no rocket forces, there's nothing at all impeding with the motion of an object. It is falling only subject to the gravitational pull from Earth. And if we identify a case that we can label as free fall, instead of the 5/3 rule, where we have 5 possible variables for our kinematics, and we need to find 3, free fall immediately fills in one of those as a known. And that known is our acceleration, because an object in free fall has an acceleration equal to the strength of gravity straight down, straight towards the center of Earth if we're on Earth, or the center of any object whatsoever. So the direction that we typically refer to as towards the center of Earth is the negative y direction. So an example of this is if you wanted to calculate the time that an object spent falling. And one of the sort of classic stunts that older time media talked about adventurers doing is traveling over the edge of Niagara Falls in a barrel and landing at the bottom and surviving. And one of the first adventurers to actually do that was named Dave Munday. And to call it a barrel, kind of like I drew here, is really misleading, because it really was more of a space capsule, because at the bottom of Niagara Falls are a lot of really large rocks. So figuring out how to stop is an important problem. And as we get into chapter 9, we'll talk about more of the physics that's needed to engineer that side of the equation. So for now, let's just calculate how much time he had to think about what he just did. So Niagara Falls are 48 meters high. And for an object that falls from rest, that means it's not moving up and it's not moving down yet. So if you just drift off the edge of a cliff, you are in free fall from rest. So free fall, our concept says that our acceleration is going to be minus the strength of Earth's gravity. And the approximate strength of Earth's gravity around where we are in the Great Lakes region is 9.8 meters per second squared. And the minus sign is because we normally think of up as positive y and down is negative y. Now, if we're falling from rest, our initial velocity is going to be 0. And if our initial velocity is 0, our change in y has to be negative. Because if we think about it, if we start up here, we end at a lower position than where we start. So specifically, our change in y is going to be minus the height that we fall. So if the falls are 48 meters tall, our displacement is negative 48 meters with an initial velocity of 0 meters per second. We have 3 knowns. So the one that we were given from free fall, plus the 2 more that we need to get up to 3. So if we take a look at our 2 unknowns, one unknown is final velocity. And it's going to be pretty important figuring out the stopping part to know how fast you're going. But if we need to know the time, we don't need to know how fast we'll be going at the end. So what I want to do then is find the family of equations where we don't need the final velocity. And that was the third equation from when I talked about kinematics using algebra, that said without final velocity, our displacement is going to be our initial velocity times time plus 1/2 times the acceleration times time squared. Now, our change in height is negative and our acceleration is negative. We will figure out those minus signs once we go to plug in the values. But first, we should just take a look at the algebra. That way we're not going to have to worry about calculating the same algebraic expressions again and again and again as we might need it in the future. So when you go to do algebra, strictly speaking, we would have to make use of the quadratic theorem to solve this. But sometimes you can get out of having to use the quadratic theorem if you start by filling in zeros. And we have a zero. Initial velocity is 0. So if our initial velocity is 0, that first term goes away, and we have delta y is equal to 1/2 times our acceleration times time squared. So to solve for time, I multiply both sides by 2, I divide both sides by my acceleration, and then to undo the square, I take the square root of both sides. So my time is going to be the square root of 2 times my displacement divided by my acceleration. Now, in math and science and engineering, there are a couple of things that should always set off a little spidey sense of danger that could happen when you're doing your math. And one of those are minus signs and a square root, because the square root of a negative number isn't a real number. And this is a real scenario. This was done successfully, so we're not going to get imaginary answers. Well, here we do get a negative sign for our displacement, and we get a negative sign for our acceleration. So those negative signs are going to cancel each other out, and we're taking the square root of a positive number. The other warning sign, as I mentioned in chapter 1, is trying to divide by something where there's a subtraction in the denominator. Because if there's a subtraction in the denominator, then you run the risk of dividing by 0. So always keep an eye out for negative signs under square roots and subtraction going on in denominators. Well, taking a look at wrapping up this problem, I have 2 times 48 meters, so that gives me 96 meters in the numerator, divided by 9.80 meters per second squared. Meters over meters cancels. 1 over second squared is second squared, and the square root of second squared gives me units of seconds. We asked to find the time. Seconds measures time, so our units are checking out. 96 divided by 9.8 gives me right around 9.8 when I calculated this out in my calculator, and when I take the square root of that, I get a value of 3.1 seconds. So that's how long Dave Mundy spent in free fall before his barrel crash landed at the bottom. Thanks for watching.